Our Chess Hub workshop, from unknowns to structures. Today we will focus on very difficult, but at the same time one of the most important parts of metabolomics. How to move from measured registered signals to meaningful, but more importantly, reliable structures. My name is Joanna Godzien, and my role in this introduction part is to give you an idea about this workshop, to basically set the scene. Why we are here, what are our aims, and how the workshop will work. So let me guide you through the structure of this workshop. After my short introduction, we will move to the two presentations given by our invited speakers, Professor Coral Barbas and Professor Huy Tang. After this, to close this opening session, Gia, who is just giving you papers with color cards, will introduce the idea of Chess Hub and its aims. Then Anisha will lead the live polling session to capture the current perspectives and challenges of your metabolomics workflow. That will lead us naturally to the breakout discussion, where we want to focus on the community requirements. Gia is now giving you color cards, and please keep them, because based on those colors, you will be assigned to a smaller working groups for the discussion part. To finish our workshop, we will have a talk given by Julian about AI and MetID. Then I will introduce the idea of MetID tool guide. And to finish, to close our workshop, Gia will come on the stage with some concluding remarks. One little disclaimer before we start. This workshop, it's not intended to be an, let's say, education workshop. But at the same time, we don't want this workshop to be just a series of separate talks. We want it to be very interactive and community-driven. So we really count on your active participation. So, without any further ado, I would like to invite on the stage our first speaker, Professor Coral Barbas from Center for Metabolomics and Bioanalysis from San Pablo University, who will give a talk about why reliable lipid annotation is important. Coral, the floor is yours.
Thank you, Joanna. Thank you. Good morning, everybody. I was discussing with the organizers that my aim in this short talk is mostly to convince all of you, if you are not convinced yet, that only annotation tools are not enough for a real annotation in metabolomics. We can know how to manage hundreds of annotation tools, but it's absolutely compulsory to have a real idea of mass spectrometry and the basis of annotation in mass spectrometry when you want to do a proper work. It's something as when you use an artificial intelligence tool to improve some work, you can do it very nicely if you know about the topic. But if you don't know about the topic, you can make a fool of yourself. So this is the same idea with metabolite annotation. So I will just show two examples of how it can totally bias your results or your work. Well, why accurate annotation matters? Because confounding a phosphocholine with a phosphoethanolamine, which is very easy, very common in a software, will change the biological explanation that you give about your work, because this will show that your work is not reliable. It doesn't matter the beautiful things that you are doing with all the rest of the work. So, as you know, and mostly in lipidomics, where the annotation is especially sophisticated and complicated due to the overlay in signals and in masses and isomers and so on, we have very different levels of annotation. And one very important point is that you use the level that you are sure you can defend. I mean, we can go from the totally unknown to the just lipid class because you know the head of the group. Or you can have the some composition of the carbons, this identification enriched with some properties. You can know the fatty acids, but not the position. You can have the exact position of the fatty acids, the position of the double bond, and finally the stereochemistry. Very often, you can see in many papers this type of annotation when they didn't do even MSMS. So you must be aware of using the level of annotation that you can really defend. Now we have many software tools to provide this annotation, and one of the aims of this group is to discuss among these identification tools which are useful, which are not anymore because they are not maintained, which is the information that we can retrieve from every kind of tool. Some are more focused in one type of structure, some on others. And it's very relevant to have a clear idea of what you are doing with them to avoid repeating some work, but also to complement the necessary information. And I would like to start with an example from our lab. We started to work with a method coming from Agilent and their database, which gave us the annotation using iterative MSMS and lipid annotation software, and a short method with 15 minutes, and we could get the quite a complete profile of lipids. And for us, this was a real interesting point because in 15 minutes, with a tool quite well developed, we could get a very good profile. When we started with our results, we always review the results manually. That is one important point. So we saw that there were two different masses with exactly the same retention time and very close percentage of change, which made us suspicious. So we started with the first annotation. We had the MSMS in positive, in negative. We could see the head group, the chains, and it was properly annotated as this phosphocholine. But when we came to the other mass, we first went to SEU Mass Mediator, which is a tool that is open source, developed in our work, in our group. Alberto, I'm looking at his face, smiling, is collecting information from many different databases and gives you just an annotation with the mass. And well, we will develop that later in a different opportunity. But we had 3 different annotations coming from these different databases that are mixed together in SEU Mass Mediator. But none of them was convincing because we know that the head of the group is a phosphocholine, so it could not be a phosphoserine. Here, your knowledge is starting to appear. Then we have an idea of the chain, so these potential annotations were wrong. We started to look at the signal, and looking at the signal, you can see that is exactly a coelution, same shape, what is important to look at. So we knew that this was an adduct that was not previously described. Well, to make a long story short, we were studying this neutral loss that is appearing here, and you need to know what a neutral loss is. The signal does not appear in the profile, but is the difference between the molecular ion and one of the signals. So with this neutral loss, this was not corresponding to any of the typical adducts, but discussing with our colleagues in organic chemistry, it happens that acetonitrile with methanol, which are part of the mobile phase, in the presence of ammonium and in the electrospray source, can produce this ion acetamidinium that protonated has exactly that mass. So this is an acetamidinium adduct of the previous molecule. So looking at all our signals, it came out that from 70 compounds, only 35 were real. All the others were acetamidinium ions or adducts of the same molecule. So that is one of the reasons why you must review your results and know mass spectrometry to check what you are doing. Going to a different story, we were working with this Syrian hamster that is a model for Alzheimer's disease. The Syrian hamster has 3 stages: torpor, arousal, and control, because they hibernate. And they have the property that when they are hibernating, they produce a situation that is similar to the one that is produced in Alzheimer's, that is, that the tau protein is dephosphorylated and they lose the organization that they have when they are awake. But there is an important thing here, that is that this situation is reversible. So if we can reach the metabolism or what is happening behind this process in the Syrian hamster, we could have some clues for the Alzheimer's disease. Of course, the tau protein is a protein. There were studies focused on the proteins, but our aim was to look at what was happening with the metabolism, the lipids and other metabolites in the brain of these animals during the process. So you can see here the work we were doing, the homogenization of the tissue, the analysis in non-target lipidomics, the use of different software tools, the statistical analysis, and finally, the interpretation. This is a summary of the lipids that we found. This is not the place to get into details, but what I wanted to focus on is in this signal. We could see that this was the most significant signal differentiating torpor, arousal, and control, and this was an unknown. This was not identified in databases. Indeed, we only could find the identification in seu mass mediator, and it was phosphatidic acid, which was totally unrealistic with the spectrum that we had for this compound. So there were no hits in the rest of databases that or the tools that we used. And coming to the MS spectra, we could see that the fatty acid had 16 carbons, not 17, but the head group had a methyl that was attached, bounded to the methyl, not to the carbon chain. So that was a new this compound was not described previously, and when we annotated it, we could see that it was not the only one, but there were several signals unknowns till this moment that shared exactly the same spectra and the same situation, and all of them were increased, were decreased in arousal and as compared to control. So this is the reason why my strong message is we need software tools. They facilitate our work. They are very important because if we have a list of more than 800 signals for lipids, we need to simplify the work, but real knowledge in mass spectrometry will make reliable your results. And that's all from my side. Thank you very much.
Do you have any questions for Coral? No, no one?
At the end.
Thank you very much, Coral, again, for your wonderful talk. And now I would like to invite for the stage Professor Huy Tang, who will give a talk about the de novo structure determination for unknown, non-lipid, this time, metabolites. So, sir, the stage is yours.
Thank you for the organizer for this opportunity. And also I was assigned a task to actually talk about structure determination for unknown, for the non-lipids. As our previous speaker actually covered the lipid already. But the strategy is the same. And the question, the problem, and the demands are exactly the same. If we don't get the right structure, you can never get the other sort of functional or mechanistic information out of that, or maybe you get the wrong end of stick anyway. So we know that for non-lipids and unknown metabolites are frequently encountered, not only in LC-MS type of study. For instance, I'll give you just one example. This is my example. We had this bioacid, and then you see there was a peak at the end of the spectra there, and there is no, it's unknown. Unknown metabolite means that you do not have a standard. You basically test all the reference standard you can buy on Earth, and you cannot match that. So it's not that. And of course, unknown, the difficulty for the unknown metabolites, there is a lot of difficulty. That's normally they are in low abundance, because high abundance metabolites has been done by our pioneers. Whatever left for us, mostly low abundance. In the case of NMR, obviously, this is NMR data for proton NMR data for rat plasma, and apart from all the signals you know, there's an unknown signal there, and of course you need to find out what they are. And if this is simple sort of situation, there are more complex systems like this. So this is a 1,000 megahertz proton NMR spectra of my urine. It's clearly a complex mixture, and I can put some labels on based on the work Jeremy Nicholson and others have done for so many years. But there are still a lot of signals in that region, especially the small ones. We do not know what they are. So unknowns, many signals with a lot of more unknowns. To actually get the absolute structure of this unknown metabolites, normally you just get a signal. Either it's a LC signal with a detector of UV or detector of MS. Doesn't really matter which one, but it's just a peak. A peak, you have to translate that into a structure. Traditionally, we actually, all people in the field and other field as well, use a technique. Basically, it's a combined technique with the chromatography, UV visible spectroscopy, two-dimensional NMR, and high-resolution mass spec. So it can be done separately. You can collect the sample, do it separately, or you can do it in a hyphenated mode. So you can do that in a way. So, for example, in this HPLC profile, there's a peak there. We've got no idea what they are. So what we do is we collect all the spectra for the UV and the mass spec. Obviously, you get the information about some information about the functional groups and the information about if your mass spec quality, data quality is good enough, you end up with a formula. Formula is not a structure. It's only element composition. And it can have many structures out of that, what we call the isomer. And then if you have the two-dimensional NMR spectra, a set of them, in fact, each one of them provide a different information. Connectively, they can actually give you information about the atomic connectivity. So connectivity of each atom. And then you end up with the formula and the connectivity, you end up with the structure. But if you have a chiral center there, then obviously you have stereochemistry there. And for instance, NMR cannot distinguish R type of amino acid and a D. So for instance, alanine, D type and L type are having exactly the same spectra. Of course, for LC NMR, MS, you probably have similar signal as well. With this traditional method, you can actually get the basically determine absolute structure of completely unknown stuff. In this particular case, we had a less than 50 microgram sample, and then you realize that in fact this is metabolites with a new skeleton. New carbon skeleton. New carbon skeleton means that there are new enzymes involved, which we do not know. And of course, in the meantime, you probably noticed that in this particular case, we've got at least 4 chiral centers there. And to think about the stereochemistry, they should have at least 16 isomers. And so which one is which one? To determine that, to the absolute configuration of a chiral center, obviously we use DFT calculation and a combination of DFT and the J coupling constants. Sometimes people use NOE as well. We don't use NOE because the combination of those are good enough. Because you know that for a chiral center, chiral carbon, it can be either R type or S type. It cannot be RS or SR or partial one because it's a quantum situation. So what you do is you actually calculate the possibility of those 16 isomers and just match the J coupling constants with your experimental value. You will find there is only one actually matched well. And now the DFT calculation actually works very nicely. So this is the way we actually were, or a lot of people are doing before. I'll give you one example we actually encountered recently. So in this particular project, we were interested in one of these enzymes, called CMD1, supposed to catalyze modification of 5-methyl cytosine. So we know that 5-methyl cytosine is the primary substrate. And after this catalysis, you just run HPLC profile, and you see all the other peaks, because we've got a standard. And apart from them, there are 2 more peaks appeared. We've got no idea what they are. And in the meantime, we do TLC, kind of very traditional, TLC type of experiment. Again, with if this enzyme is wild type, you have 2 extra spots that we know. We call that the P1 and the P2, product 1, product 2. So the question is, what are they? If we don't know the structure, basically research stops there. You can report that the discovery of 2 new things, anonymous things. Of course, we were interested in their identity, so we just do LCMS and for the standard and this product, and you end up with the accurate mass. Therefore, the formula like this they are new. And then if you do MSMS, so second, fragmentation, you start to see a major fragments come from those new products, as those two share exactly the same precursor and the same fragments as well. So they are most likely isomers. And if you look at this 216 and the molecular mass of 332, the difference is actually come from a deoxyribose. We know it's related in that way. Those two new products have the exactly same fragmentation pattern, but very different one from known metabolites of cytosine or methyl cytosine. So we go further, and we just look at this fragment because we don't have to worry about the deoxyribose anymore here. And you can see from that fragment, if you just heat the iron, it lose 3 water. Therefore, there should be 3 hydroxyl groups in the remaining part of the molecule. Of course, you can label this methyl group as a CD3, and then you have basically 2 units extra. Therefore, it's likely that one of the hydroxyl group is not attached to this methyl group, but that's only likely. So we just work step by step. By this step, we just thought it should be, the fragment should look like this. But then you have 2 possibilities. Basically, you've got a trihydroxyl propyl residue actually attached to methyl cytosine. There are 2 possibilities. One is that obviously you've got 3 hydroxyl groups linked to those 3 carbon. The other one possibility is that it's that way. Of course, there are other possibilities as well, so that you still get whatever information you have earlier. So this really reminded me that you rely on MS alone, you cannot get a structure. So we still ask this question, what are they? The only possibilities do NMR. Of course, in our case, you just run a proton NMR, you get a J coupling constant will be useful later. And of course, a set of 2-dimensional NMR. Normally, this 5 will provide enough information for you. And for product 1, product 2, you just go through. And of course, you analyze the spectra carefully. That's all. I'm not going through to the details. And once you accumulate enough experience, everybody can do that. And based on 2-dimensional NMR data, we eventually realized that the linkage, atomic linkage, is really related to this one. Now, we have 2 chiral centers there. And there are 4 possible isomers, according to Van Hoff theory. So what we did was we know that there are only 4. It's either RR or SS or RS or SR. That's the only possibility. And with a structure like that, you just use these DFT tools to work out the J coupling constants, and then match with your experimental one. And eventually we found that, in fact, for P1 and P2, they are in this way. Of course, this is not enough, because it's completely new. And this is very convincing for me already, but not convincing for everybody. So eventually we actually did total synthesis in collaboration with a synthetic organic chemist, synthesized all 4 of them, and basically matched the chromatography, mass spec, and NMR data. Eventually, we determined is that. So once you actually have this absolute structure, then you can talk about mechanisms of biosynthesis, where they come from, and potential functions and a mechanism for functioning these functions. So really, for structural determination, if we just stayed in a certain level 2, level 3, that's not enough now. It may be good enough in 1950s, when technology actually basically exhausted their capability. Now we should really go a little bit further and try to get the absolute structure if it is a new one, especially if it is a new one. So I hope that I showed you the necessity to get the absolute structure and roughly how we can get there. If you want to get the absolute structure, the take-home message is that it's a combination of several techniques. And a single technique cannot always solve our problem. With that, I thank you for your attention.
Thank you very much. Do we have any questions? Yeah?
Good morning. Thank you very much for your talk. This is kind of a question for you, but also the previous. I have a hunch that a lot of our unknowns are bacterial-derived, and that's why they're so absent from our databases. We have a lot of mammalian biology covered, but bacterial is the wild, wild west. So curious about panels. I know there's more talks coming, but curious about your perspective on whether we think that's what the giant dark metabolome, or a lot of what it's composed of. But now getting to the NMR part, I love NMR, incredible technology, but it's so less sensitive than mass spec. How do we get over that massive gap in terms of starting to dive into biological data to get NMRs of these unknowns? Oh. Sorry, should I repeat all of that again? Or hopefully I projected well enough.
I actually understand what you said.
Great.
Thank you. I think your microphone actually answered your question already. In old days, NMR is insensitive, like that microphone actually worked earlier. And now it can be sensitive. It can be sensitive. For microbes, metabolome microbes, obviously there is extra dimension, and plants as well. There's an extra dimension of complexity. Basically, they have not only secondary metabolism, but also a lot of metabolites which we actually haven't actually get into certain depth. So far, if you can get all the available reference standard, and then you can basically confirm whatever you found. And for the unknown, completely unknown, basically means that you cannot have a standard. And then the only thing, if you really want 100% sure, you have to probably do total synthesis. That's what we normally do. And of course, depends on how important that question is. If that's depends on the scientific question you want to answer. If you don't know the structure, but you can answer the question already, then you probably don't want to make an effort there. I don't know. I mean, for a curiosity of science, obviously, you want to go to the bottom of that. For the sensitivity of NMR, you probably noticed that with the 600 megahertz NMR, that's quite common now, you can actually determine the absolute structure of a small molecule, meaning molecular mass is smaller than 150 Dalton, with 10 micrograms. So 10 micrograms is, I think, it's a small amount. Although if you have to basically collect them, basically prepare with. In fact, you use analytical HPLC column, you can actually get enough for that. If you have a semi-prep, you get milligrams easily. We don't work on milligrams anymore because that's really the technology we used when I was still doing my PhD a long time ago. I only partially agree with your statement that mass spec is a lot more sensitive than NMR. It depends on the compound that you are looking at. I'll give you an example. If you look at the butane, you probably notice that the mass spec will be extremely insensitive. I was educated as a mass spec person, so I basically learned my NMR by myself. So there are sort of complementary aspect of those two. Of course, NMR is insensitive. Normally, 600 megahertz can only, for the pure compound, you only detect something around, 5 macromolar sort of concentration level. But now, with the sensitivity enhancement, you can go down to 20 nanomolar. So my guess is that, of course, with the effort, one day, 20 nanomolar is fairly close to mass spec. NMR basically responds uniformly to all sort of analyzed. That's probably a good thing. But having said that, we cannot solve all our problems with any technique, or even with a combined technique so far. But the only thing we can do is we can make an effort to going towards that way. It's like this chess activity, I guess. I hope I answered your question.
Yeah, actually, maybe I can just add to what Can you hear me? Oh, yeah, just to add to Hiru's answer. So you're absolutely right. Not just bacterial, but other microorganisms. There's a fungal metabolome. So a lot of the reference libraries and databases that are available for the community to support with identifying metabolites are based on endogenous metabolism, but there's a whole wealth of exogenous sources of metabolites that we will also find in biological samples. These can be from diet, they could be from medication, as well as, the microbial co-metabolites. So I know a lot of groups are working on identifying some of these unknowns that we are finding in our biological samples, and perhaps that could be an initiative for us as well to try and bring those together to be able to consolidate all of that work that's going on. Because you're right, I think we have a set of information. We know, physiological metabolites, but there's a whole dark world of these exogenous metabolites that we need to work together to help us to understand what they are.
Before I forget, I'll just add that the most difficult one is some of the metabolites are not terribly stable in vivo. And obviously, any technique we use, normally we involve with the extraction process. By then, they probably has been changed into something else. We have to be careful about that. Thank you.
Okay, thank you very much. And now, due to time restrictions, we are moving to the next talk, finishing this introduction part, where Gia will tell you about the Chess Hub.
Thank you, Joanna. Good morning, everyone. My name is Jiali from Imperial College London. I'm the chair of the Chess Hub. I'm going to briefly introduce the hub, but I think, the Professor Barbas and Wijeyesekera Tang have beautifully illustrated the power and the complexity of MetID. This is really a challenging but critical bottleneck in metabolomics if we want to move metabolomics forward for clinical or epidemiological applications. So I think this is probably also one of the bottlenecks, I would say the hardest, the most technically challenging, and perhaps also the most underfunded and under-resourced bottleneck. So I think this is why the Chess Hub was established last year in November, aiming to address some of those challenges, and especially combining expertise from different areas like analytical chemistry, biochemistry, organic chemistry, and like Wijeyesekera demonstrated, the combination of NMR and mass spec for MetID, this is really crucial. So I think we have very clear aim for the Chess Hub. It's a community. We wanted to advance the field of chemical structure elucidation for MetID and biomarker discovery through collaboration, knowledge exchange, and the training, which is a really important component highlighted by Barbas. So really our mission is to strengthen the metabolite identification for translational metabolomics. So in details, we wanted to promote 5 different aspects. We want to promote methodological innovation and best practice. We will also organize different events. This will be space for us to interact, sharing our practice ideas, and also collaborate. Certainly, we would like to
facilitates the open access to training and material and databases, like the question asked, different databases address different type of samples, different source of the samples. We also would like to encourage cross-disciplinary exchange among the academic, clinical, and industry, even regulatory communities. I think those challenges in MetaID may be seen differently by, different identities of the people. So putting all different perspectives into the same room would definitely be beneficial. And lastly, and also I feel really strong about, is to support the early research careers. I think combining with this platform, with this hub, a community-based hub, we can train and nurture the next generation of MetaID experts, which would be really crucial for the growth of metabolomics. So I think I'll stop here for the time constraint, and then we can move to the next session. Thank you.
Thank you. Now I would like to invite Anisha for our next part, which will be live polling session.
Okay, so then the next part of the workshop is really for us to work with you to identify what you already know about Metabolite ID, how you approach it in your work, where the gaps are, what you find challenging, and really an opportunity for us to better understand where the science is at the moment. So to help us with that, we have set up an online poll. So if you go to woocollab.com, and the event code is CHESS 2026, but hopefully we can get the QR code up on the screen. There it is. Thank you. Thanks. So I'll give you a few minutes to log in and to start to answer the questions. The first few questions is really just information gathering. So as Joanna said at the start, we've got a breakout session coming up. So just for us to understand who we've got here in the workshop, what stage of your careers are at, and what your current understanding of MetaID is and how you currently approach it. So the first 10 or so questions are really just for us to gather some information. When you get to question 10, which talks about Metabolite ID tiers, I will pull up some slides to help you to answer those if you're not sure. Right, so when you get to question 10, just in case you're not sure about the question talking about levels, we've put some slides together if that helps to distinguish between the difference between the confidence levels. So we give some examples of MSI-4, MSI-4+, or the Szymanski 5, or the NMR tiers. So if that helps to answer that question, I'll just leave up these slides. So I'm not sure how far you've got, but I'm just going to go through some of the first questions because it looks like some of you may have finished. So who is here in the room? We have got quite a few LCMS users, a few NMR, a bit of a mix. The other will want to know what other, out of curiosity. In terms of role, does the software stop? Have you been able to answer that question? Yeah, okay. I don't know why. Maybe you need to refresh it. There we go, okay. Oh. Strange. Okay, then the next question was about your experience in analytical chemistry. I don't know why the answers aren't here, because I can see that they've been answered, but okay. Organic chemistry, biochemistry, and computer science. Why is this thing so weird? Yeah, I think maybe this is not updating in real time, so we might just go to our breakout rooms, and then when we come back, I can show you the results of the poll. But thank you for answering those questions. It's going to be really useful for us to think about as we go into the breakout rooms, to think about what some of these challenges are, where the gaps are, and where we could work together to try and tackle them. So I think we're going to move to that next.
With this, we will move to our next session, which is breakout discussion. Okay, so now you have the list of 4 questions, and we want you to discuss them, to exchange your experience, to exchange your opinions. We will give you around 30 minutes to discuss all these questions, and then it would be super nice if you could delegate, one of you or maybe 2 people can share the main outcomes of your discussion, so we can see if your maybe perspectives or experience are different than perspectives from other groups, okay? We want to see the landscape of the expertise, the landscape of perspectives, the landscape of needs that we are having here, okay? So, enjoy. Okay, guys, I see that you are still discussing, and it's really tough for me to break this discussion. But due to the time limitations, we have to move to the next part. If now, if from each group, if there is someone who wants to share the main ideas or the main home message taking from your discussion, that would be perfect. I would like to ask to give this little summary in 1 or 2 minutes, so we can have enough time for Jewel talk before the time of our workshop finish. Okay? So, is there any group that want to start?
We were discussing, I think one of the main outcomes was about library coverage for during LCMS workflows, and also regarding the bottlenecks, the time to analyze the results and all the spectral matches and get information from literature and make sure that even though library coverage has like numerical back support, but also make time to take the time to analyze your results and make sure they are authentic, like actually correct, and that is also a bottleneck. Also regarding prioritizing the knowledge from the biological background and context within the results, and also connecting bioinformatics with biologists and chemists, so we can also like harmonize the languages between bioinformatics and the chemistry side, even within our same lab or with other groups. And also regarding training, more training related to bioinformatics, because sometimes for us chemists or biologists, we need to know Python, R, or coding, and sometimes we are lacking experience in that, so more opportunities regarding webinars or training could be very beneficial for us. But also maybe bioinformaticians or computer science people, when they are talking to us, sometimes they don't know the structural prediction is this, but then what is this? Like, so then we need to communicate more with them and intensify our efforts in that area. And then we have more about vendor companies or licensed databases, the lack of methods or lack of tools for unified data conversion formats between all the companies. That is like one of the biggest drawbacks, or that will allow to standardize the pipelines and also facilitate reporting, data sharing. Yes, okay, yeah. Anyone else that wants to add something? Yes.
Biased, I'm a bioinformatician. So I think also looking into benchmarking these machine learning approaches, which now, like, say we can go from peak to structure, and yes, that's great if that will work, but at the moment they're like, literally they pop up like mushrooms, and I'm not really sure how well they perform also in comparison to a person doing the job. And I think that's something we have to figure out, because if they work great, then I think that's what we want to use.
One more thing, if you can share with us the notes that you took during this session, that would be absolutely fantastic, because maybe we can somehow summarize them and share with all of you afterwards, okay? Our idea was that each group will share the outcome of your discussion, but unfortunately we have to move to the next part. So one more group, just few words about home-taking message. Alberto, yeah?
So, well, thank you very much to the organizers. And yeah, we were discussing most of the things, but we think, or we agreed that we should tackle the problem from the first moment and working on assigning all the signals generated by a single metabolite will help in the identification, and going to concrete actions that we can do in the Chess Hub initiative that you have here is introducing a reporting guidelines like we have for lipids, and providing the confidence base in two aspects: the analytical aspects and the biological aspect, as the other group mentioned, will be great for improving the reproducibility and the trustability in metabolomics. So thank you.
So we will move now to the last part, and I would like to invite on the stage Julian. And before, once again, thank you very much, and ovation for all of you.
Yeah, so I'll try to be brief, and there is, in the sake of time, but also because I don't bring answers, I bring more questions and more challenges. So I will just discuss, or I was asked to discuss how we can harness the power of AI to help us with MetID. And it is a hard talk because, to be honest, it changes every month. So it's very difficult, and that talk is the one of today. And if you would have asked me 6 months ago, I would probably come with a different answer. But we all we know what we want annotated quantities, absolute concentrations. That's what we want, that's a fact. And we know that it's difficult to get there because it's difficult to model the peak, so it's difficult to actually get proper extractions, but it's also very difficult to know for sure that we are picking the correct signal. So there is a few challenges. And I think we've heard a lot today, but the point is, I don't think we can build database that will always work. By definition, we will always find in nature somewhere where it breaks, and maybe we have to think of systems that help us doing the job very quickly, but also are very clever to stop when something is interesting going on. So for example, everybody will recognize the glucose peak on that. I don't know if there is a marker. I mean, at least in the NMR community, we've been trained to recognize that signal. We use it for many, many things and calibration. But then if I tell the students to analyze not serum sample, but bowel samples, then he will actually find the same doublet, and he can't possibly know that there is a hidden maltose. It took us all by surprise, and we had actually to review our own method. So intrinsically, I'm looking at something that I know I've seen in thousands of samples. Then I just swap the sample for another one. I see exactly the same feature. Everybody would actually conclude the same thing. But it was wrong, and there is a maltose superimposed. We have the information. We can find the solution, but it takes what Coral says, a bit of understanding of the method. So we can go so far as characterizing and summarizing, OK, when you look at this, you know that it's glucose. It's true. Sometimes it breaks down. Other things, yeah, we look at we look at some real samples, and we start making a database about, for example, tyrosine, tyramine, and it works in hundreds or several hundreds of samples. Then you find one where you have a third peak. And the question is, how do we actually train models to be able to recognize one from the others? When we have three, it's easy because I know that I have to annotate 3 compounds, but when I have only one, it becomes very difficult. So we will always find a situation where the context is required, and the question is, if we don't have this expertise and the people in the lab to give that context, it's very difficult to build systems that are very reliable. Now, there is no question that AI will help us. And actually, we probably all did the same thing. So you put just the capture and say, what is this? And I mean, the AI today is actually pretty good. But at some point, he will ask, OK, so what is the matrix? I haven't copied all the things. It goes for pages and pages for the same. Because OK, I say stool samples. Then he changed his mind, I mean, logically. But he would have asked me before. No, he hasn't. And then I suggest that it might have forgotten something and then come with something else. My point is, it is useful, it will be useful, but the question is how do we provide AI context very efficiently? Because in the end, it will behave very much as we do. We need further information. So what next? I would say, okay, what about? And then the conversation goes on. What is the next part of the spectra you would like to see in order to confirm your initial guess? So that's something like this. So we would like to ask, can you check the assignment and find the reference compounds? Or can you use a Stoxy analysis, something we do in the lab? I won't go into the details to actually make sure that we are assigning the proper signal. Or maybe can you also check in the KEGG database if what you propose actually makes sense from a biology perspective, knowing that sample. And we can have a list of other tasks that we would like to do. And if we do that currently, it won't work because maybe he doesn't know where to find those reference spectra, and maybe because he doesn't know what is the tool I want to use for the visualization. But and the system are changing very quickly, we can introduce the idea of skills. So we can train the AI by giving this context and to some extent change the behavior. So by just letting the model know about where I would like him to check, so I put some databases that I like, and then I maybe prioritize them, and then by explaining what is NMRM, which is actually a free tool to use on the web, I can tell him to interpret my initial call, this very simple one-liner without any context, and the context is given by the skill. So he reads NMRM, he reads reference spectra, and he will actually load that context and provide me within roughly 30 seconds the file, the zip file, that I can drag and drop into the NMRM and get everything annotated. So this is just a stupid plain example of how we can start transferring skills of something that I can do on my own. I can go click, download, and prepare the things together. But then I can just train the AI to do it on my behalf, and then I can just shortcut and use this little line of prompt, and then he will do it for me, and then I can use it for whatever. But we can extend that much further and give him more context, more skills to actually use our own tools. Now, that's the point. We have to make sure that this context can be shared and reproduced. Now, we can do that, and what is cool about AI today is that it works at different levels. So we can also train and give tasks within the browser for the AI to use the tools. So this is going a bit further, and then I can prompt something like this, where I can ask him to create a screenshot or something that can be used to feed into the next chat, and we can actually loop this way, and then he can check for himself. If I give him where my data are and so on and so forth, I can help this model to go and check and get the visualizations he wants and confirm the annotations. So as I said, I don't know if this will evolve further, because 6 months ago I was not playing with skills, now I am. And then it gets the next question. So for example, from a MetaID community, how can I share my skill? When something works for me, then I can transfer it to another, it will work. There is some problem, so it changed, it's very dynamic today, obviously. But there is no standard on how to write. There is no metrics to actually assess how well my skill is working for my case or for yours. And we don't know if they will work equally on each model that we are using. Either model meaning the Claude, ChatGPT, or whatever we are using to read those skills. But skills are text documents, so maybe we can share them very easily, and we can use all the versioning system for codes. So we could have a community set of shared skill that we can download, pick, and try see if it works. So there's something that we can definitely discuss if there is an interest of doing that. And I think the main takeaway message is this can work because we already have, I mean, databases. We have reference databases thanks to all the work that has been done. And we have also cool tools like NMRium or other pipeline, Python script and everything. And then we can glue that together in a way that maybe will help us do our job faster. I've heard a lot of complaint today that most of the time we just stop because we don't have the time to go further. Now, if I can train an agent to do something of a pretty good job and send thousands out there to do that in a few, overnight, then in the next morning I just have to review and see what makes sense. So I think there is plenty of way to work with AI. I think we will have to learn very quickly, but today skills seems to be something interesting to discuss in a community like ours.
I think what is very important, apart from all the possibilities that AI can bring to the metabolite annotation, is that finally you can send dozens of agents to work for you during the night, but next day you have to review them. Yeah, that we cannot skip this this part. So. Coming to the end of this workshop, I would like to introduce briefly the idea of MetID tool guide. Over last 10-15 years, we observe an explosion of different tools, software, and approaches for metabolite annotation. Each of them is addressing a different challenges, different limitations, and is approaching metabolite annotation from a very different perspectives. And we are now having a very complex ecosystem of different softwares and tools, which undeniably is a powerful and it's a strength of the field. However, this complex environment is increasingly challenging to navigate, especially for young researchers or less experienced people or non-specialists. And sometimes it's difficult to decide which tool we should use to address which problem, which type of data we need to put in, and what type of evidence we will get out of the tool, of the software, and how to interpret the outcome of the analysis performed, what level of confidence it's assigned to a given results, and finally, which tools we should combine to have enough evidence put it together on the table to come to the robust and reliable annotation. So, considering this huge ecosystem, we would like to somehow help navigate people through this ecosystem. The idea of this guide came partially from a lipid guide tool that was established and connected resource on the lipid maps, although it's focused on lipidomics and it's navigating through different tools that we can use on different stages, on different stages of lipidomics workflow. It's a very nice example of how we can navigate the very complex landscape of softwares, how we can clearly categorize them, and finally how we can present them to the community. So our idea is to prepare, being inspired by this lipidomics tool guide, we are considering to do something similar for the softwares, for tools, for platforms dedicated to metabolite annotation. So we want to catalog available tools, curate them, because there are dozens of wonderful solutions that unfortunately are not supported, are not available anymore, then to categorize them and perform a guide that will navigate researchers through those softwares. Obviously, it's a huge amount of work that cannot be done by a single person or even single group. Furthermore, we don't want this effort to be done by a single group, because then it will reflect the perspective of a single group and will address the needs of a single group. And probably you saw very clearly during today's breakout discussion how different our perspectives are, how different our experience is. So with this, I would like to invite those of you who are interested in joining us in this effort to be a part of this work. If you are interested, please drop me an email. My email is in the end, or approach me during the conference. If you personally are not interested in this effort, in this initiative, but you believe that someone from your group, your colleagues might be willing to join this effort, please pass them my email, okay? So with this, thank you very much. And Gia, I will invite you to close our workshop.
Thank you. I know we're overrunning a little bit, so I'm going to keep very brief. So thanks all very much for being here today, and it's really a pleasure to see all of you and having such a wonderful discussion. I feel bad actually to interrupt that. I actually wish to have a bit more time. And we got quite a lot of exciting ideas for the Chess Hub to going forward, so that's really great, so thanks again. And I'd like to also thank all of the presenters, the speakers, for the wonderful insights, and also the Chess Hub committee members that putting this workshop together. Thanks very much. And at the beginning, we give you a form, registration form. So if you wish to join us in this community, please fill the form and return to us, and we'll keep in touch. We also have a website. There's no QR codes on this, but it's okay. So if you Google this name, and you should be able to find, and then there's email address. If you have any ideas that you wanted to share with us, please send us an email. Thanks very much again.